Hi there. In this video we're going to talk about geometry, transformation, and determinants in R2. We'll learn how to convert a linear function to a matrix, we'll visualize a linear transformation, and we'll relate the determinant of a matrix to an area. Let's get started. So first we're going to look at how to convert a linear function into a matrix. So consider this guy. Right? For any x and y that we plug in, we're going to get 3x plus y, x plus 2y. And we want to find a matrix that represents this linear function. So what do we need? We need that this matrix, when you multiply it by the vector xy, has the same output as the transformation when you input the vector xy. Right? We want this matrix to behave the same way as our linear function. So this puts some pretty severe restrictions on what our matrix can look like. Right? We want to fill in the matrix here so that it behaves the same way as our linear function. So let's look at this first row. When we plug in the vector xy and multiply it by this matrix, we want to get 3x plus y. So we need to put a 3 here and a 1 here so that the 3 multiplies on the x and the 1 multiplies on the y to give us 3x plus y. Now let's look at our second row. We want to get x plus 2y. So we need something that when we multiply it against xy gives us x plus 2y. So we need to put a 1 here and a 2 here. When we multiply these rows against the column xy, we're going to get the exact same thing that we have on the right-hand side. Okay? One way to think of this process is we take the coefficients in the matrix on the right-hand side and we put them into the matrix on the left-hand side. Okay, now we've got a matrix that represents our linear function. Let's sketch the effect of AT on the square with these sides. Okay, so we're going to take AT times E1, right? That'll be our matrix times E1. And notice what happens when we compute this. Now we're multiplying 3, 1 against 1, 0. And 1, 2 against 1, 0. When we do this matrix multiplication, we're going to get the vector 3, 1. Okay. Similarly, when we do the matrix multiplication against E2, we're going to get 1, 2. Okay. One thing I want to point out about this process is that this matrix multiplication extracts the first row, or sorry, the first column of our matrix, right? When we do this multiplication, the answer is that first column. Very, very important fact, very, very helpful to remember that multiplying against E1 extracts the first column of the matrix. Okay, now let's sketch the effect of this linear transformation on the square with sides E1, E2. So the first thing to do is to visualize what E1, E2 look like. Right? We draw the vector E1 here. And the vector E2 here. Okay, so our E1 is our x-axis and our E2 is our y-axis. And this forms a little square, right, with corner 1, 1. Okay, so we'll just label all of the corners of this. Okay, now let's see where the linear transformation takes that square. So we know that the vector e1 gets sent to the vector 3, 1. And the vector e2 gets sent to the vector 1, 2. Okay, so now we want to ask ourselves, where does 1, 1 get sent to? Where does this top right-hand corner get sent to? Right? If we do the matrix multiplication, we're going to see that this gets sent to 4, 3. Okay, so what happens is this square gets shifted and distorted into this parallelogram. Okay. Very good. So we see that matrix multiplication causes some kind of change to the unit square. Now, it's interesting to ask, how does that change the area of the unit square when we apply this matrix multiplication? Let's have a look. We'll find the area of the parallelogram determined by 3, 1 and 1, 2. Now, thinking back, we've got a formula for area of parallelograms. Can you remember what it is? The area of a parallelogram is the cross product of its sides. Okay, so let's take the cross product of those sides. Notice that the cross product's defined in R3, so we've added on a 0 here because these vectors live in the plane. But that doesn't change the area of the parallelogram. Now when we calculate the cross product, we get that it's the vector 5, 0, 0, and taking lengths, we have something of length 5. Now there's a subtle connection I want to point out here. We have this area, but let's look at the determinant of the matrix AT. We also have the following fact, that this is the determinant of 3, 1, 1, 2. Calculate that, we get 6 minus 1, which is 5. Coincidence? Perhaps. Suppose that we had a matrix that satisfies the following. The matrix sends E1 to AC and E2 to BD. I encourage you to use the reasoning that we've done here with parallelograms, the cross product, and the determinant to see if there's any relationship between that area and the determinant of the matrix M. Good luck!